Separation of variables is the most common and probably the easiest way to solve a differential equation. First, what is a differential equation? It's just an equation that has a derivative in there somewhere. This top equation here is a differential equation. Why? Because it has this derivative, dy over dt equals ky, and you need to solve for y. Let's look at this specific differential equation, because this is probably the most common differential equation in math class. It is certainly probably the most common differential equation in nature. It's something that you see a lot. Let's first understand what it's saying. It's saying dy over dt, that means the rate of change in y with respect to time, or how fast y is growing, is equal to k times y. In other words, is equal to some constant times the amount of stuff you have. So in other words, the rate of growth, how much new stuff you're getting every second or minute or whatever, is proportional to the amount of stuff that you have. You see this all the time, just everywhere. Bacteria in a petri dish. The more bacteria you have, the more new bacteria come into being every second or every hour, minute, whatever. Why? Because if you have more bacteria that are dividing at some particular rate, the more you have, the more new ones you're going to get after a minute or second or whatever. We see the same thing in banking. The more money you have in your bank account, the more dollars of interest you're going to get per year or per month. In other words, once again, the rate of growth, the amount of new stuff you're getting, is proportional to the original amount of stuff. Very, very common situation. You see it everywhere. Here's something else that you see everywhere, that you've probably seen these equations, these three identical equations, a lot. Sometimes you see it written like this: A, which means the amount, equals A sub O, which is the original amount, times E to the KT. Sometimes you see it in economics, finance, whatever, interest, as A, or the amount, equals P times the principal times E to the RT, or to the rate times time. Same basic equation, obviously. In chemistry, we sometimes write it in as N, the number of particles equals N sub O times E to the RT. You can also do this with moles in chemistry. These equations are all the same, and they actually all derive from this differential equation. Now, when you were first looking at these, you're like, why are there all these E's? Now that you've done a bit of calculus, you see how often ln shows up. Well, all those times that ln shows up, that's where the E's are coming from. In this next worksheet, you're going to you're going to figure out how this very simple, differential equation that describes so many things in nature then produces these exponential growth equations, which also describe those exact same things in nature. The method you're going to use is called separation of variables. You'll see why it's called that. It should be pretty obvious by the end. This is really the most important differential equation in nature, and you're going to see how it connects to these major equations that you should already have seen before.